Hello everyone. So today we're going to be learning how we can convert a CFG into a PDA. So first, let's have a quick recap of what a CFG and what a PDA is. So CFG is context-free grammar. It refers to a four-tuple, usually denoted by G, and it is given as NTPS, where N is the set of non-terminals, T is the set of terminals, P is the set of production rules, and S is the set of, or just the start symbol. And today we are going to be learning how to convert this CFG, which often renders the CFL, which is often known as context-free language. And that context-free language is accepted by a machine or a mathematical abstract model known as PDA or Push Down Automata. So this Push Down Automata is denoted by a 7-tuple M, K, sigma, tau, delta, Q naught, Z naught, F. We have discussed PDA to CFG conversion in detail in the previous video, which was the tough part. But CFG to PDA is a very easy and a very straightforward, simplified manner if you can understand what CFG and PDA essentially are and how they work. So we have already discussed it in the previous video that a PDA works on the principle of stacks. Therefore, we have stack symbols. And hence, we usually take in the different amounts of the different symbols that are fed to us from the CFG, and then we push it down into the PDA. That is the stack symbols that we are inserting into the PDA, right? So in this video, we're going to be tackling the problem of CFG to PDA conversion, which is context-free grammar to push down automata conversion. And we are going to take in two aspects of this problem. So there are two main aspects of this CFG to PDA conversion. One form is when CFG is present in a non-GNF form. So you might be familiar with GNF, which is Greibach normal form, and it is a form where every terminal is followed by non-terminals, and every non-terminal derives a terminal. So you can see this question here. This grammar is present in a Greibach normal form. Here, this grammar is not present in a Greibach normal form. So this is a non-GNF GNF form. Here, the second part of CFG to PDA conversion is the GNF form. So here we are going to tackle both of these problems, and we are going to learn how to solve them one by one. So let's first start with the non-GNF form. It's a pretty easy task as well, and GNF makes it even easier. So now let's see how we can convert that, right? So for the first part, let's start by solving this question and learn on our way. S goes to ASB and F goes to, wait, this is AS small b. Yeah. And this is A goes to AB, S goes to AB. So these are the two production rules that we have been given for our CFG, and now we have to derive a PD out of it. So now let's start by defining the transition functions. So the transition functions for this are pretty easy. We need to first think about pushing the elements in. So for pushing the elements in, we are going to make use of our transition function with an input symbol null for pushing at first, and then we are going to add on things onto it, and then we're going to see how the entire mechanism works. So first of all, the first transition function that we have with us is Q epsilon S is equal to Q and ASB. The second one we have is Q epsilon S is equal to QAB. Can you sense a pattern here? When we are starting something, there is nothing that we have to input, but there's a starting state that we have. So on this stack symbol, we are adding ASB, which is our push function, because these are the only two ways we can push and add something into our production, into our PDF. So this is how we are going to tackle this problem. And then we have two more functions to see if the given stack or the given stack is empty, and then we are also going to see if by the end of this entire production our stack is emptying itself or not. So the third production rule we have is Q A A. So since input symbol and the stack symbol are both the same, we can say Q is epsilon, and then for our fourth production rule, Q B B, this is also given as Q epsilon. So these are both pop functions. We have already discussed it in this previous video of our PDA to CFG conversion. You can check that out as well. Push functions, and this is the pop function, right? So in our first push functions, we have with us these two rules, and in our pop functions we have these two rules. Now let's see how the PDA is going to be defined for it. We have already defined the production rules, which was the tough part. Now let's come on to the easy one. So this is our PDA, this is our stack for the PDA. Now let's see how it works. First of all, when there is nothing at the bottom of it, and let's take a sample string, okay? The sample string is A B B B, for example, okay? So this is a part of this. We all know that this grammar is corresponding to a to the power n, b to the power n, where n is greater than equal to 1, right? It's because s is ASB and then ASB and then AB at some point. So yeah, this is the kind of string that we are going to be seeing and checking if it abides by it. So now, first of all, when there is nothing to input and there's only a start symbol there, so we are going to add A S B, right? So B S A, A S B. And then, so our A has been already input. So now let's see this A that was already input here is on top of an A, right? So when there is nothing to input and there is now an A on top of this A, we are going to remove this A, and then we are going to add B S A again on top of S. So when there is S, we add A as B, S, A as B. So we're going to remove this B as well, and then on top of this S also, we are going to add B, S, A. And now for our final A, we again pop out this A according to this rule, right? And then we have a null symbol and an S again here. And now that we can see there's an AB here, so this is a very classic example of a non-deterministic PDA, better known as NDPDA. So this is something that we are doing on our own will, and we have the freedom to explore the different types of strings that can be made with it. And now that we have come to a conclusion that okay, A and B both are available with us, and now we have to end this entire string of A's. So we have again taken a null symbol and an S symbol, and then we add on this, we replace this S with the help of B and A again. Now that we encounter a B, we remove this A and then we go on to this symbol. So this B is on top of the B that is already there. So according to our rule, we pop. Then again, we come back to the symbol. There is a B on top of a B, on top of a B. So we pop again, and there is again a pop symbol here. So we have already popped these two, and then there's a B on top of a B again. So we pop this B again. So our push down automata is empty. Our stack is empty. Therefore, we have reached the state of acceptance. So when our stack is empty, we can say that we have reached a state of acceptance and there is nothing left as to process now, and we have already accepted the string that is given to us. So for all these examples, it's going to work in a very similar way. If even we would have taken triple A or a 4 times A and then 4 times B, it would have worked a very similar way. First of all, we input the starting symbols, then we go on to the adding more symbols on top of A as B and so on. So this is how things work in the non-GNF form. Now let's move on to the GNF form, which is even simpler. So GNF form is working on these lines. So let's copy this question here again. So second part says that, the second part says that S goes to 0, B, B, and B goes to 0, S, 1, S, or 0. So this is all that we have right now. Now, let's start by seeing how the transition functions for this can be defined. So first transition function that can be defined for us is delta Q0S going to QBB, right? Because Q is the starting function, S is the symbol that we have encountered, the start symbol, and 0 is the input symbol. Now, the second transition function that we can define here is Q0B, which is going to Q and S. We are done with this production rule as well, and then Q1B goes to Q and S. So we are done with this production rule as well, and then delta Q0B goes to Q and null. So this here is a pop function, and these are all push functions. Now let's see how this PDA will function, how this stack will be characterized, and let's see how this works. So for the sake of our consideration, we will take a string that is accepted by it. Now let's take the string 0, 1, 1, 2, 3, 4. Let's see if it is accepted by it. So S starts with 0, B, B. So yeah, S starts with 0, B, B. B goes to 1, S. B goes to 0, S. S goes to 0, S goes to 0. So yeah, 0 and 4 times 0 is also accepted by this entire production rules, by this grammar. So now let's start by using this push down automata, and by using this these production rules, these transition functions, to make up our stack and see how it checks out. So first of all, when there is nothing, we are going to input a 0 as we have encountered it. So 0 is encountered and there is a start symbol. There's nothing else than a start symbol here. So we are going to turn this start symbol into a BB. So start symbol we remove and then we replace it by a BB, right? Then we come across a 1. This was done, this was processed, now we come across a 1. So this 1 is processed and we encounter a B, and this B is changed to an S, right? B changes to an S. Now we have also processed this 1. Now let's come to our 0. So this 0 is on top of S. So this production rule again, S goes to S turns into a BB again. Great. We have processed this as well. Now, as we can see from these production rules, this side of these two rules is the same. So what we can conclude is that this is also an NDPDA. This is also a non-deterministic push down automata, and we can take the rules as we want them. So now we are encountering one more 0 here, and this is on top of a B. So instead of replacing this B again with an S, what I can do is that I can simply just pop this B out of it in order to have my empty stack back, right? So this B here is popped on encountering this 0. So I pop this B and now I'm left with 2 more B's. Now I come across this 0, and again what I do is instead of adding something, I come here and I pop it again. So now I'm left with my last 0 and I'm left with my last B here, my last B, my last plate, which after which if I pop this again, I pop this, I am left with an empty stack, which finally accepts, which is finally the state of acceptance, the ultimate acceptance for my string into the PDA. So this is how you can design and implement PDAs with the help of CFGs, and how you can essentially convert a CFG into a PDA. Thank you so much for watching. I hope you understood the entire concept of converting a CFG into a PDA by these two methods, and when these two situations are given to us, if there is a non-GNF or if there is a GNF form, and then you have to implement these and check if the stack is empty at the end, because our final state is an empty stack here. Thank you so much.